Ladies and gents, we're going to take a look at the last part of Unit A. It might not look like it's the last part because there's a bunch of pages in Unit A, but there's additional problems at the end. And then there's also a bunch of pages in terms of how to do this in Excel. And the labs will actually be better for that, but it's got the procedures that you would use for using the analysis tool pack. But we want to take a look at this one last test in Unit A, and it's the Friedman's two-way non-parametric Anova test. Kind of a scary sounding name there. But here's what it's all about here. You use a Friedman's test when you've got a question about ranking. So a lot of your surveys that you're doing for your project have ranking questions. So for instance, what are the top reasons that you've chosen our particular restaurant? And then you say, assign a 1 for the top reason, and 2 for the second most important reason, and 3 for the third most important reason, and so on like that. So whenever you're dealing with those ranking questions, the Friedman's test is the guy you want to use for that. And it's similar to a Kruskal-Wallis, but it's, well, we'll see the difference as we go through here. So the second paragraph down here says that the Friedman's test is similar to inform to the KW, except that the numbers are not all ranked together. We actually rank each row separately. And that's because if you take a look at the way this would be set up on a spreadsheet, is remember on a spreadsheet for the data set, you've got every row represents a respondent. And then what you'll have is a column for each of the different possible categories that you're ranking. So if you ask them to choose their top 3 out of, say, 5, you'd have 5 columns. And you'd be putting in numbers 1, 2, and 3 across a particular row. And obviously you want to keep those numbers together because they're all for a particular respondent. So that's why we call it a two-way ANOVA. It's not just according to the different classifications or things that you can rank, the categories that you can rank in a question, but we also want to recognize that anything in a particular row is for a particular respondent. So let's take a look at the form of the hypotheses here then. Is all of the items are preferred equally. You would probably change that into words there for depending on what the problem is there. And then the test statistic is, you can see it's very similar actually to what you've got there for Kruskal-Wallis test. The only difference in terms of this though is that the N here represents the number of observations in each treatment. So we're talking about the number of respondents is probably the best thing to think of. Now, it's not always people, of course, that you're sampling, but for the types of things that you'll be doing for your projects, it is. So the number of rows that we have here then. And then the other numbers are ones that you have seen before here. Rejection region is always upper tail chi-square with k-1 degrees of freedom, just like in a Kruskal-Wallis test. And steps 4 and 5 are similar. So let me show you an example of this. I want you to think of this as being a typical data set that you would see in Excel. So we've got our respondents down the side. I've actually named them ABC up to J. So we've got 10 persons or 10 respondents. And they've been asked to rank their choice of movies here. And so 4 movies were given, and then they said, the question said, what's the order of preference? So what's your favorite movie of these 4? Give it a 1. And your second most is a 2, third is a 3, and a fourth is the least preferred of these. So that's how the thing would be set up. And let's go through and actually work through this particular problem here then. So step number 1 is all items are preferred equally. So in our particular case, the items are the movies. So we would say that all the movies are preferred equally. Against the alternative that at least one movie is preferred more or less than the others. So it could be a much higher rating or a much lower rating. I guess a lower rating in this case would be a more preferred movie, right? Because your most preferred movie is giving a low number. So that's important to note when you're talking about preferences like this. A low number means it's more preferred. A higher number, it's less preferred. The test statistic that we're going to use in this particular case then is 12 over n times, I'm going to take a look back at this one here. I don't use this a lot. N times k. No, let's just do it this way. N times k plus 1. And then we're going to have the sum of the rj squares. Now you don't have to divide through by an nj because they're actually all divided through by the same n, or they all have the same n in this particular case. Minus 3 times n times k plus 1. Let me just check that formula again. It's not one that I do a lot by hand. And that looks good. Okay. Step number 3 is that this is a chi-square test. Always upper tail. So in our particular case then, it's going to be a chi-square with, how many movies are we at? 1, 2, 3, 4. So it'll be 4 minus 1 is going to be 3. And actually we saw that in the last video here, is that turned out to be 7.81. And that would be for an alpha of 5% here. Okay. So if chi-square star is greater than 7.81, you're going to reject HO. I'm going to assume that you know how to find that number on a chi-square table. If not, come and see me. All right, step number 4. What we do is we go here and we sum up the ranks. Now, it's really important, and I'm going to talk about this in the next little bit here when we're finished this problem here, but it's really important that for any particular row here, that they sum up to k times k plus 1 divided by 2. So in our particular case, that would be 4 times 5 divided by 2 is equal to 10. All right? And if you take a look at this, if they have ranked them correctly, that should work. 1 plus 2 plus 3 plus 4 is equal to 10, so you're good. This one's pretty clean. Actually, every row adds up to 10, but that's something that you need to check. And I will say that I've got in the Anova template, you can just simply take the numbers and stuff them in, and you'll see that it'll take care of any errors that you have there with some few exceptions, and I'm going to talk about that in a moment. But let's get back to our problem here. So once you've got, for every row, you've got the numbers 1 to 4, like this, then you sum up to come up with the RJs here. So the sum of the movie 1 ratings here then turns out to be 21. And then the sum of this column turns out to be 20. And this one is 30, and this is 29. Now, when I take a look at that, I say it looks pretty obvious to me where the differences lie. However, you'll find that actually I don't think that you end up rejecting HO in this particular case. So we're going to have step number 4 This, of course, is part of step number 4, is adding up the RJs. And so we're going to have this chi-squared star is equal to 12 over n. Now the n in this case is 10. So there's 10 people here. There's not 40 numbers. So that's the difference between the NT of a Kruskal-Wallis test and the n here of a Friedman's test. All right, so that's really important that you note that there. Times 4, which is your k, 4 movies, times k plus 1. And then what you do is you take these green ones here, sum of the RJs. So 21 squared plus 20 squared plus 30 squared plus 29 squared minus 3 times 10 times 5, which is k plus 1. And that turns out to be 4.92. Now, 4.92 falls in here, and so, of course, that means that you are not rejecting HO. So what we have is 4.92 is not greater than your critical value, and therefore do not reject HO. So what this is saying here then is that there actually are no significant differences between the ratings of the movies here. While we're here, you know I like this kind of stuff. The critical value, of course, would be found by a chi-square dot inverse right tail, always upper tail, 0.053. And then over here, your p-value is going to be sorry, that should be chi-square, there we go, is equal to chi-square dot dist dot right tail 4.923, and that actually comes out to about 18%. So that 18% is greater than 5%, and so you would not reject HO. All right, now I just want to continue on a little bit here because unfortunately this often turns out to be messy, especially when it is a survey which is done by paper, and so people are filling these things out using paper. If you're using something like Google Forms or SurveyMonkey or something like that, then it actually forces them to choose their first, second, third choice and so on like that. And so it comes out pretty clean. But if this were a paper copy, which they're filling out themselves, people always mess this up, and it can be quite frustrating. So let me give you an example here. We're not going to actually work through this particular problem. You can do that if you want to, but I want to focus on how you clean up the rows here. Suppose the question is asked in our survey here. Rank in order the following 5 television networks in order of personal preference, with 1 being the network you most prefer to watch, 2 the next preferred, down to 5 the least preferred network. By the way, that's a great way of writing the actual question there. And so the 5 networks are going to be CBC, CTV, NBC, ABC, and CBS. All right. So we've got the first 10 respondents look like this. Now, what I want you to notice about these ones here is that remember that each row must add up to k times k plus 1 divided by 2. So in this particular case then would be 5 times 6 divided by 2 is equal to 15, which are just the numbers 1 plus 2 plus 3 plus 4 plus 5. So we take a look at this, and what we see is that this is good. Person 1 did it correctly. Person 2, person B did it correctly. But person C only ranked their top 2. And that's actually probably okay. In fact, what I would probably add at the top here in the question is don't rank a network if you never watch it. And so in this particular case, then, they only have 2, 1 and 2. So what do you do with the rest here? Well, what you'll notice is that they add up to 3. 1 plus 2 is equal to 3, but it should add up to 15. Now, you don't want to leave it blank because remember, a 1, a low number, a 1, is considered to be the most preferred. And so if you leave it blank, actually, the numerical value of a blank is 0 when you use the machinery here of the calculation, and you don't want that. So you actually want to put a number in there. So what you do is, just like you were doing with a Kruskal-Wallis test, except that we're just doing it across a particular row, what you do is you look here and you say, okay, 1, 2, I've got a tie here for the 3rd, 4th, and 5th numbers. So 3 plus 4 plus 5 divided by 3 numbers there, gives us an average ranking of 4. Okay, so what we would have here then is the 3rd, 4th, and 5th values would have an average ranking of 4. Now, when you add those up, 1 plus 4 plus 2 plus 4 plus 4, you get 15 there. So we're good. Sometimes what you find is that people will checkbox these instead of putting in a number. So if you take a look at person D here, what they've done is they've put in 1 check, and that's for CTV. So what we do is we change that to a 1. And then what we do is we say, okay, now they're indifferent between the other ones. And so we've got 2 plus 3 plus 4 plus 5, divide that by 4, right? The average ranking of those 4 would be 2, 3, 3.5. So they would be 3.5s, right? So they got 1, but then 2, 3, 4, and 5, the average ranking of those are 3.5. Okay, the next one here is, this is somebody who checkmarked 4 of them and left 1 blank. So what we have here then is that they've got 4 that they watch. They're indifferent between them. So they would be your 1st, 2nd, 3rd, and 4th values. So 1 plus 2 plus 3 plus 4 divided by 4 values gives them 2.5s. So they would have 2.5s, the average ranking of the first 4 numbers. And then this one would be a 5, so that it adds up to 15, right? The next one is they're all checked. And so it would be the average ranking of 1 plus 2 plus 3 plus 4 plus 5, so they'd all get 3s. Like that. Now, the next one is a very common mistake here. What people do is they'll look through this and they'll say, I really am indifferent between CBC and CTV. As long as it's Canadian channel, I'm good. And so they're my first choice. And then after that, well, ABC and then CBS and then NBC I never really watch. So what we do here is we say, well, actually, just like in a Kruskal-Wallis, but again, just by row, we'd say the 2 1s hold the 1st and 2nd position. We can't really distinguish between the 2, so they are average rankings of 1 and 1.5 and 1.5. But they take up the 1st and 2nd positions, so we can't have a 2 here. We got to change this to a 3. We got to change this 3 to a 4, and this becomes a 5. So similarly down in the next one, the 1, so we're taking a look at person H. The 1 is okay, the 2 is okay. The 2 3s take up the 3rd and 4th positions, so they would be 3.5s. And then the 4, of course, would be a 5. This particular person, we would just take right out. And you might wonder, well, why are they in there anyways? Probably because they actually answered other questions on the survey, but they just didn't answer this question. So we would just take them right out. And then the last one here is 1, 2, 3, 4, and we would put in a 5 here for ABC. So now all of them add up to 15 going across here. And I've done that down here. We'll see. By the way, if you're using the Anova file, then just simply put in the numbers as they are, just as they come, but change the checks to ones. So don't worry about what the average rankings are and stuff. I've actually built the thing so that it'll take that into account. So the ones such as say H and J and so on, G, H, and J, where they mess up the numbers, but at least they're still numbers, just leave them the way they are. But the ones that have checks, change all the checks just to ones, and you'll be okay. And then you'll use the Anova template, and I'm going to show you a little video on that, how to do that. But anyways, this is what we've done down here, down at the very bottom here. And so that's how you would handle that if you had to do that by hand. But again, I've got a template that will do that for you, and I will show that to you in a lab video. The rest of the chapter is just how to do Anova using Excel. So there's a little video on that, a lab video on that, and I've also talked about that in class. That's the one-way Anova. We're not going to be doing two-way ANOVAs, but this is how you would do that for the Alberta and Pine Tree ones. Now, in this particular case, we only have one pine tree in Alberta. This is two-way with replication. So this is two-way without replication, only one number in each of these cells. And two-way with replication is this one, where, and this again is still fairly simplistic, but we have 3 pine trees from Alberta and 3 of each of the others. Now practically we would probably have, maybe 100 pine trees from Alberta or something. But this is how you would actually do that. And if you ever run into that, you're not going to be required to know how to do that. The additional problems down here are one-way and two-way problems. I'd like you actually just to have to do the one-way ones. So the first one is a one-way Anova problem, and you can do that one by hand. Number 2 is good. Number 3 is a two-way problem. You don't have to do that one because it's actually just a duplication of number 1, but as a two-way. Number 4 is good. You can do that one. Number 5 is a one-way Anova. What you could do is just simply ignore this and use the Anova template for that. So do this by hand and then use the Anova template and see if you get the same results there. And the same for number 6 as well. Okay? So you could do those ones actually as just one-way ANOVAs. And there you go. So the answers here then for some of them are two-way ANOVAs, and you can certainly see how it works on that. So when you get down to number 3, for instance, we've got 2 F-tests here. But that will take you through to the end of the unit. And so that ends the unit. Thanks for watching.